Welcome to lecture 41, the last lecture for this course. Awesome, you've made it. All right, so we're 12.2, test for independence and the homogeneity of proportions. So notice we are just going to be looking at independence. We will not be looking at this for this section. Now, we're going to look at an inferential method to determine whether an apparent association between two categorical variables is statistically significant. So we're looking for whether an apparent association between two categorical variables is statistically significant. So for the first objective, we're going to perform a test for independence. All right, by definition, the chi-square test for independence is used to determine whether there is an association between a row variable and a column variable in a contingency table constructed from the sample data. So for example, if you're trying to think of something right here, is there association between smoking and lung cancer, right? Those are two categorical variables, and is there an association? That'd be something we could look at. So, the null hypothesis is that the variables are not associated, or they are independent. For example, smoking does not affect your lungs. Or the alternative hypothesis is that the variables are associated or dependent. Maybe smoking does affect your lungs. Just an example. So the expected frequencies in a chi-square test for independence. So to find the expected frequency in a cell when performing a chi-square independence test, you're going to multiply the cell's row total by its column total and divide this result by the table total. So that is the expected frequency is going to be equal to row total times the column total divided by table total. So now we have two different ways to find expected frequency, but for 12.1 we were only working with one category, and 12.2 we have two categories, so our expected frequency calculation has changed. Now in the book there is a bit more of a greater sort of explanation on how this formula came about. If you want to read that, that is on page 528. But this is the formula we'll be using. So for example 1, fill in the row, column, and table total for the following data. Alright, so this is leading up to finding the expected frequency. Well, the row total. Alright, I'll go ahead and calculate that. So I'll just go ahead actually and write these down so you see where the calculations are coming from. So we're taking them across the way to find that total right there. And then so we'll add the 33. And we'll do the same for the other ones below. And then to find the column totals, you're going to add them downwards. So this would be the 593 plus 4 plus 169. So on an exam, more than likely a table like this will appear. The work you see where I'm adding it, I would like to see you write out the addition, so you're showing me where you're getting the answer from. As usual, you're proving to me that you know how to find the answer, and that you know the method for finding the answer, not just the actual answer. To be able to clearly write out what it is you're doing is part of the SLO, student learning outcome, for this course. So to be able to communicate clearly in mathematics is important, not just finding the answer, though the answer is important. Okay, so once again, showing the addition is something that I'd like to see on a chart if it shows up on the exam. I'll go ahead and pause the video and fill these out and check back in with me in a second. Okay, so I went ahead and I found the totals. So I found the row totals, the column totals, and the table total. And remember, the table total comes from adding up all of the inside values there. All right, so now we're going to use this to find the frequency. It's the expected frequency. Which is going to be equal to the row total times the table total. Sorry, not times the table total. Times the column total divided by the table total. In our case, our table total is 939. Okay, so I'm going to do a few with you, and then I'll have you guys do them on yourself in a sec. So we're looking for intended and less than 3 months. Well, intended and less than 3 months, so the total for intended is 652, and the total for less than 3 months is 826. So we'll go ahead and multiply those together. 826 times 652. And then we're going to divide that by the table total, which is 939. And let's see what we get. Okay, so rounding it out to the 2 decimal places, we'll end up with approximately 57354. Alright, I'll set up one more for you, and then I'll ask that you pause the video and try them out by yourself. So the next one we're going to find, let's do unintended and up to 5 months. So that box we'll be filling out is this one right here. So unintended and up to 5 months. Let's see, the total for unintended is 83, and the total for up to 5 months, or sorry, 3 to 5 months, is 53. 3 to 5, not up to 5. Okay, well the total for intended was 83. Total for 3 to 5 months was 53. And we're going to divide that by the table total, which is 939. And what do we get? And we get to with approximately 4.68. Alright, go ahead and pause the video. I'll fill out the chart and check in with me in a second. Okay, so I went ahead and I filled in the formula for all of the following. Once again, this is how I'd like you to show your work for your charts. So after that, we'll go ahead and calculate out the values. So if we had 652 times the 53 divided by 939, we would get 36.8. And the next value, we would get 41.66. Then unintended and less than 3 months is 73.01. Skipping, we get unintended and more than 5 months, so 5.3. Then mistimed and less than 3 months, 179.45. Mistimed and 3 to 5 months, 11.51. And then mistimed and more than 5 months, or never, 13.04. Alright, so there we have the expected frequencies for all these values. Now, let's take a look at the test statistic for a test of independence. Alright, so we're going to let O sub I represent the observed number of counts in the ith cell, and E sub I represent the expected number of counts in the ith cell. So we have the observed and then the expected, which we have seen before. So then we have the test statistic, which is pretty much the same as before. The sum of O sub I minus E sub I squared divided by E sub I. And this approximately follows the chi-square distribution. And now this is where it changes up a bit, we have R minus 1 times C minus 1 degrees of freedom. So the degrees of freedom has changed because we're comparing 2 different categories now. And R is the number of rows that we have, and C is the number of columns that we have. And this is all provided that, 1, all the expected frequencies are greater than or equal to 1, and no more than 20% of the expected frequencies are less than 5, which we have seen that before. So real quick, counting up rows and columns, let's take a look here. How many rows do we have? Well, we have 1, 2, 3 rows, and how many columns do we have? We have 1, 2, 3 columns. So we could go ahead and calculate out the degree of frequency for that. Now let's take a look at the chi-square test for independence using the classical approach. Once again, we have classical and p-value approach, and basically the difference is how you use the table. So to test hypotheses regarding the association between or independence of 2 variables in a contingency table, use the steps that follow. First, you're going to determine the null and alternative hypothesis. Then the row variable and the column variable for our null hypothesis is going to be they are independent. That means they don't affect each other. The alternative would be the row variable and the column variable are dependent, or they do affect each other. So then you choose a level of significance, alpha, depending on the seriousness of making a type 1 error. Often, remember, alpha is given to you. And then for step 3, there are 3 parts. First, you're going to calculate the expected frequencies for each cell in the contingency table. B, verify that the requirements for the chi-square test of independence are satisfied. Pretty much just check that they're greater than 5. And if any of them are less than 5, only 20% can be less than 5. Then you're going to compute the test statistic, which we've seen before. Chi naught squared is going to be the sum of the observed minus the expected squared divided by the expected. And step 4. So, determine the critical value using table 8. All chi-squared tests for independence are right-tailed. So the critical value is our lovely symbol here, chi-squared alpha, with r minus 1 times c minus 1 degrees of freedom. Once again, our degrees of freedom have changed because we're looking at 2 different categories, where r is the number of rows and c is the number of columns in the contingency table. So once we found that, we're going to compare the critical value to the test statistic, basically the same steps we've been looking at previously. And if we find out that our test statistic is greater than our critical value, then we reject the null hypothesis. And at the end, we'll state the conclusion. Alright, so those are the steps for the classical method. Let's take a look at these steps for the p-value approach. Once again, the first 2 steps are basically exactly the same. Things start to change up in step 3. So, to test the hypothesis regarding the association between, or independence of, 2 variables in a contingency table, we're going to use the steps that follow. First, determine the null and alternative hypothesis. So for alpha, the row variable and the column variable are independent. It means there is no connection. And the alternative, the row variable and the column variable are dependent. Step 2, once again, choose a level of significance alpha depending on the seriousness of making a type 1 error. Now, our steps here, step 3, this is where things change up. We have 4 steps here. First, you're going to calculate the test, or the expected frequencies, for each cell in the contingency table. B, you're going to verify that the requirements for the chi-squared test of independence are satisfied. Once again, basically everything greater than 5, and if any are less than 5, only 20% can be less than 5. Then you're going to compute the test statistic. So really, up to this point, the classical and the p-value are pretty much the same in how you're computing this. Both of them, you find your test statistic, which you find the same way, but it's pretty much just how you use it and how you use the table that differs. So for step D, use table 8 to determine an approximate p-value by determining the area under the chi-square distribution with, we have the same type of freedom, r minus 1 times c minus 1 degrees of freedom, where r is the number of rows, strange gap right there, gotta fix that, and c is the number of columns in the contingency table. And step 4, if the p-value is less than alpha, then we are going to reject the null hypothesis. If not, we can't reject it. So step 5, we're going to state the conclusion. Alright, so now let's take a look at example 2. So, an obstetrician wants to learn whether the amount of prenatal care and wantedness, strange word, our textbook uses that word, but my computer didn't think it was a word. So I don't know. So the wantedness of the pregnancy are associated. He randomly selects 939 women who had recently given birth and asks them to disclose whether their pregnancy was intended, unintended, or mistimed. In addition, they were to disclose when they started receiving prenatal care, if ever. We computed the expected values for this in example 1, so now we're actually going to use them. So these were the values that we computed in example 1. So we've already found the expected frequencies. Now let's go ahead and test them. First, though, we need to verify the requirements for performing a chi-square test if independents are satisfied. Well, let's see. We do have one value that is less than 5, but that's only 1. But let's make sure that this is not greater than 20%. So how do we figure that out? Well, we have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 values. So 1 out of the 9 are less than 5. What is 1 out of 9? That's about 11%. So we're good. 5.3 is greater than 5. Okay, so we've checked. They're all greater than. So what's our sentence going to be? Well, only 11% of the expected values are less than 5. And all are greater than 1. So that's a good sentence. Make sure to indicate either that they're all greater than 5 if they are, and if any of them are less than 5, indicate what percent are less than 5, and then also state that the rest, or all of them, are greater than 1. So now we're going to go ahead and compute the chi-square test statistic. Once again, the chi-square test statistic, we have that is equal to the sum of our observed values minus our expected frequencies divided by our expected frequencies. So what do we have in our table? Well, for the intended and less than 3 months, what was our expected frequency for that? Let's head back to the chart up here. The expected frequency, all the way back here, was, it's going to be the 593. Okay, so we'll go ahead, write that down. That's our observed value is 593, I think I just said. Alright, so we have 593 minus the expected, which is 573.54 divided by 573.54, and we square that, plus, and we'll go ahead and find the other values. Alright, so go ahead, try fill these out, and I'll fill them out as well, and check in with me in a second. So we'll get approximately 21.38. Okay, so there we have our test statistic. Now, we're going to go ahead and use the classical approach to test whether prenatal care and the wantedness of pregnancy are independent at the alpha equals 0.05 level of significance. Okay, so for the classical approach, remember what we do is we test to see if our critical value is less than our test statistic. If it is, then we reject the null hypothesis. In order to find that, though, we need to know what our degree of freedom is. So the degree of freedom is going to be equal to r minus 1 times c minus 1. And remember we discovered earlier that r was 3 and c was also 3, the row and column. So then we end up with 2 times 2, which is 4. So our degrees of freedom are 4. Let me go ahead and insert our table here. So we have our table, our chi-square distribution. We're looking for degrees of freedom equal to 4. Let me go ahead and highlight that. And then we're looking for alpha of 0.05. So right here, where do they intersect? Well, they intersect at 9.488. Okay, so we found that our chi-squared alpha is going to be 9.488. And our degree of freedom was 4. Let me go ahead and box that. So let's compare. Our test statistic was 21.38. Is that greater than 9.488? The answer is yes, it is greater than. So since it's greater than, we're going to reject the null hypothesis. Alrighty, so we can state because that was greater than the critical value, we reject the null hypothesis. There is sufficient evidence at the alpha equals 0.05 level of significance. To what? Well, to conclude that wantedness of pregnancy what does it do? Wantedness of pregnancy and months pregnant before prenatal care are associated. So, and months pregnant before care are associated. Squeeze that in. Okay, so we found out that there is a relationship. If the person actually wanted their pregnancy, they're more likely to have gotten prenatal care sooner. Kind of makes sense, but now we've proven it statistically. So now we're going to use the p-value approach to test whether prenatal care and the wantedness of pregnancy are independent at the alpha equals 0.05 level of significance. So once again, it just changes how we use our table. Alright, so I've included the table. Now, how do we use the table for the p-value approach? Well, the p-value approach, you're going to look at your level of, you're going to look at your degree of freedom, which we already found. Let me just note that here. The degree of freedom is still the same, which was 4 from above. So we'll look for the degree of freedom, 4. And in this degree of freedom, we are going to look for the p-value closest to our test statistic. Well, the closest value that we see, remember our test statistic was 21.38. So in actuality, it actually is bigger than what we have in our chart. So we're just going to pick the closest value we see to it, and the closest value we see to it, or our closest p-value, alpha, is going to be 0.005. So our p-value is not going to be equal to 0.005, because remember, that is not the actual value we have. It's actually going to be less than 0.005. And is this less than our alpha? Well, it is. It's less than our alpha. So since, and it's less than our alpha, which is 0.05. Alright, so with p-value, we're comparing our alpha to our p-value, and since our p-value is less than, we're going to reject the null hypothesis. So since our p-value equal to 0.005 is less than alpha equal to 0.05, we reject the null hypothesis. So what does that mean? Well, basically the exact same thing as we stated above. So there is sufficient evidence at the alpha equals 0.05 level of significance that wantedness, to conclude that wantedness of pregnancy and months pregnant before prenatal care are associated. Okay, so that was the two different ways to look at it. We used the p-value or the classical approach. And more than likely, I'll state which approach I want you to use on an exam. So here's a question. Where is the biggest difference between the observed and expected values? The biggest difference. Let's take a look up here where we're subtracting them. So which one has the largest difference between the observed value and the expected value? Well, if we're to go ahead and compute the differences between all of these, the one that actually has the greatest difference between the observed and expected value is this one here. That difference is 19.46, which you don't actually need to know the real number, but it is greater. So if you were to compare all the different subtractions, this would be the greatest, which was 19.46. So that's the greatest difference, and that is the intended and less than 3 months. So what would my answer be? Well, where's the biggest difference between the observed and expected values? The biggest difference is between, intended, and less than 3 months. And you can go ahead and include the difference, which was 19.46. Alrighty, so there we go. Alright, and you can review constructing bar graphs on page 533. I didn't cover that here because I'm pretty positive we've covered bar graphs good enough, or well enough. And note, we do not cover Objective 2, performing a test for homogeneity. Okay, that is not something we cover for this course. Well, that is it. Please email if you have any questions about studying for the final, or any questions on this specific section.